Chapter 5, Section 1, Area Under the Curve. I'm your host, Dr. D. Okay, here we go. Now, the study of calculus is broken up into differential calculus and integral calculus. We have completed differential calculus. Limit theory, derivatives, that's differential calculus. The second portion of the discipline of calculus is called integral calculus, and we are beginning right now. So, integration deals with the area under a curve. Now, let's say our curve is a straight line, like y equals 3. And I want to know what's the area under that function between x equals 1 and x equals 3. Well, clearly, this is a rectangle. Its base is 2, and its height is 3. So that makes the area 6. Now that's fairly easy because the function is a straight line. Now if we had a function that was a curved line, we'd have either a triangle or a trapezoid. Equally simple. What if, rather than a straight line though, what if we have a curve? Now we want to know the area under that curve. From x equals 1 to x equals 3. How do we do that? Well, this is a much different story. So, let's check out a function that we know. Let's check out a function that we know. Come. There we are. Okay. So we have the function y equals x squared, and we want the area of this function under the curve between 0 and 1. So that's going to look like this. Now, we know from integration that that area is exactly 1/3. But we're about to find out how to determine that. So now we know the area of rectangles. So what if we take rectangles and use them to estimate this area? Now I have 4 rectangles here. These are called left-handed rectangles because the left corner of each rectangle touches my curve. So now if I estimate these using the rectangles, the first rectangle goes from 0 to 1/4. Then the second goes from 1/4 to 1/2. Then from 1/2 to 3/4. And then from 3/4 to 1. Now the height of each rectangle is going to be determined by the function itself. Since this curve is y equals x squared, then how high is it right here at x equals 1/4? Well, it's 1/4 squared, which is 1/16. And at 1/2, it's 1/2 squared, so it's 1/4 high. And at 3/4, it's 9/16 high. So I can calculate the area of these 3 rectangles and add them up. And then I'll have an estimate of the area under the curve. Now, what if I use more rectangles than just 4? Like, let's say I use 10 rectangles. What's that going to look like? obviously, using 10 rectangles, we have a better quality estimate. It's not as much error under the curve. What if we use 50 rectangles? So our error has gone way down with 50 rectangles. What if we use infinitely many rectangles? Yes, what if we did that? If we had infinitely many rectangles, then we would know exactly the area under the curve. And our calculator is actually capable of doing that for us. And that would tell us that the area under this curve from 0 to 1 is exactly 1/3. Okay, now, let's take a look at, I showed you 4 rectangles to begin with. Let's go back to 4. And these, like I said, are left-handed rectangles. What if I used right-handed rectangles? These are now right-handed rectangles. Notice the right corner of each rectangle touches the curve. Now, let's actually calculate the areas of these. So, for a left-handed rectangle, what we're going to do is L sub 4. That means 4 rectangles, all left-handed. So we have, notice the width of each rectangle is 1/4. So it's going to be delta x, which is the width, times f of x, which is the height. So the width is going to equal 1/4 on each rectangle, because we're going from 0 to 1, and there are 4 rectangles, so it's 1 divided by 4 is 1/4. Times, now what's the height of the first rectangle? 0. The height of the second rectangle, 1/4 squared, 1/16. The height of the third rectangle, 1/2 squared, is 1/4. And the height of the last rectangle, 3/4 squared, which is 9/16. So L sub 4, the area with 4 rectangles, is going to be 1/16 plus 9/16 is 10/16 plus another 4/16 is 14/16. So that's 14 over 64, or 7 over 32. That's the area of L sub 4. Now, what if we do R sub 4? Let's see. Yeah, R sub 4. So we get rid of the left-handed rectangles and put in the right. Now what's our area going to be? Well, R sub 4 is going to equal 1/4 again, times the height of the first rectangle, which is 1/4 squared, plus the height of the second rectangle, which is 1/2 squared, plus height of the third rectangle, which is 3/4 squared, and the last rectangle, which is 1 squared. So R sub 4 is going to be 1 plus 9 is 10, plus 4 is 14, plus another 16 is 30. So I've got 30 over 16 times 1/4, let's see, do that right? Yeah, 30 over 16 times 1/4 is 30 over 64, which is 15 over 32. So notice L sub 4 is an underestimate, R sub 4 is an overestimate. Now there's one more type of estimate that we're going to do today, and that is called a midpoint estimate. The midpoint estimate, let's go back, show, here's my right-handed rectangle, or I'm sorry, my left-handed rectangles, where the left edge of the rectangle hits the curve. Then my right-handed rectangles, where the right edge of the rectangle hits the curve. Now what about when the midpoint of each rectangle hits the curve? See, notice the midpoint of each rectangle hits the curve. Now here we have a little over and a little under. A little over, a little under. A little over, a little under. A little over, a little under. So this is a more accurate estimate. So now, if I want the midpoint estimate for 4 rectangles, once again, each rectangle is 1/4 wide. Now the first rectangle is how tall? Well, it hits the curve at the midpoint between 0 and 1/4, which is 1/8. So the function is x squared, so it's 1/8 squared, which is 1/64. The second rectangle is going to hit at 3/8 squared, which is 9/64. Then this third rectangle, the midpoint is at 5/8. So that's 25/64 tall. And the last rectangle would hit at 7/8, which is 49/64. And so when we add all these up, we've got 10, 35, 84 over 128. I'm sorry, 84 over 256. Which is 4221 over 64. So the midpoint estimate is in between the left and the right. And, like I told you before, the exact correct answer is 1/3. So notice it's pretty close to 1/3. If that was 21 1/3 over 64, that would be exactly 1/3. So we know how to get a left-handed estimate, a right-handed estimate, and a midpoint rectangle estimate for our curves. And we could do this with any amount of rectangles. Because like if I wanted to do the 50 rectangles, how wide is each rectangle? Well, it's 1 minus 0 is 1 divided by 50. Let me put that up here on the board. The width of each rectangle, delta x, is always going to equal b minus a over n, where n is the number of rectangles. So our width is 1 minus 0 divided by 4 is 1/4. But if we put more rectangles in or had a wider area, then it would change the width of each rectangle. Okay, now, okay, the next thing we want to do is, we've talked about estimating the area under these curves. Now what we want to do is find the exact area under these curves. So what we're going to do then, instead of having 4 rectangles or 50 rectangles, we're going to have infinitely many rectangles. Yes, infinitely many. Okay, so let's do that. Okay, the area under our curve is going to be the limit as n approaches infinity of the summation from I equals 1 to n of f of x sub I delta x. Now, what this means is I'm summing up infinitely many of these height times bases, because I'm counting them from I equals 1 to 2 to 3 to 4 to 5 to 6 all the way up to n. How many n's are we having? Infinitely many of them. Okay, so remember we said the delta x each time is b minus a, which is the right side minus the left side of the interval, divided by the total number of rectangles. So what we do here then is we say b minus a is 1 in this case, and n, we're letting that be infinity, so we're keeping it n. So each rectangle is 1 over n wide. Now what's the height of the rectangle? Well, it's going to be that number squared. So my first rectangle is going to be 1 over n squared. Now the second rectangle, we now have 2 of those, so it's going to be up the curve a little higher, so it's 2 over n squared. Third rectangle is 3 over n squared. The nth rectangle would be n over n squared. So this is what we're summing up, infinitely many of these. So cruising onward, the area then is going to be the limit as n approaches infinity of the height of each rectangle. So here we are, 1 over n squared, 2 over n squared, 3 over n squared, 4 over n squared, 5 over n squared, all the way up to n over n squared, times the width of each rectangle, which is 1 over n. Now, notice what I can do is factor out of each one of these terms a 1 over n squared, and that leaves me with 1 squared plus 2 squared plus 3 squared plus 4 squared all the way up to n squared. And then we have our 1 over n part out in front. Okay, now, from Algebra 2, you remember that we have these shortcuts for summations. Like if I'm summing I equals 1 to n of 1, then I'm adding 1 plus 1 plus 1 plus 1 plus 1 n times. Well, n times 1 is n. Now here I'm adding 1 plus 2 plus 3 plus 4 plus 5 plus 6 all the way up n times, and that's going to equal n times n plus 1 over 2. So just for example, if I go I equals 1 to n, where let's say n is 10, so 1 plus 2 plus 3 plus 4 plus 5 all the way up to 10, that's going to equal 10 times 11 over 2, which equals 55. Piece of cake. Now, the third shortcut that you should remember from Algebra 2 is summation from I equals 1 to n of I squared, which is 1 squared plus 2 squared plus 3 squared plus 4 squared up to n squared. And that's going to equal n times n plus 1 times 2n plus 1 all over 6. Well, this is exactly what I did right here. Can I have 1 squared plus 2 squared plus 3 squared up to n squared? Well, I'm just going to put that in right here. Now, the other thing I did was I took my 1 over n here, multiplied by 1 over n squared here, and I have 1 over n cubed here. Now, we still have the limit as n approaches infinity of all this. And this is going to be our exact area. So, next thing, I'm going to distribute all this junk and end up with 2n cubed plus 3n squared plus n all over 6. Now, I'm going to take each term separately. 2n cubed over 6 is n cubed over 3 times 1 over n cubed, just 1/3. And then 3n squared over 6 is n squared over 2 times 1 over n cubed, that's 1 over 2n. And then n over 6 times 1 over n cubed is 1 over 6n squared. Now, as I let n approach infinity, the 1/3 stays 1/3, 1 over 2n goes to 0, 1 over 6n squared goes to 0, and so my area equals exactly 1/3. Thank you, Andrew. All right, that's enough. Okay, so this isn't something that you need to be able to do immediately. It's something we're going to be doing next section more in detail, but I just wanted you to see how that works. So we can actually get an exact area under the curve. But your task for this section is to be able to do approximate areas under the curves using the right-handed rectangles, the left-handed rectangles, and the midpoint rectangles. Now, which type of rectangle do we use when we're using infinitely many? Let's think about this. If I'm using infinitely many rectangles, then how wide is each rectangle? Well, it's going to be 1 over n wide, where n is infinity. So that means each rectangle will be infinitesimally thin. So that means whether it's the right side, the left side, or the middle of this infinitesimally thin rectangle, it doesn't even matter. So when we're doing infinitely many, right, left, middle, whatever, is completely irrelevant. Okay, now, the last thing we're going to do is look at this in terms of a distance. See, we know that distance equals velocity times time. Distance equals velocity times time. So if I have a curve where I have velocity and, oops, wrong way, take two. I have a curve where I have time here and velocity here. Now here's a object that's traveling. Its velocity is getting higher and higher, so it's going faster and faster. Now it's slowing down a little bit, but it's still moving forward. And now it's speeding back up just a little bit. That's what this particle is doing. Now, what if I said, I want to know how far this thing has gone from point A to point B? How far it's gone? Well, that means I need velocity, which is the height, times time, which is the distance. So, velocity times time equals distance. So the distance is the area under the velocity curve. So, if you look at example 4, notice we have an odometer that is telling us, we have an odometer that's broken. Yeah, we don't know how far we're going. We know the velocity at given times. So, at every 5 seconds, we know how fast we're going. But we don't know how far we've gone. Now, okay, so we've got miles per hour initially, but since our time is in seconds, we want our velocity to be in feet per second. Because when I go velocity times time, feet per second times seconds equals feet. But if it was miles per hour times seconds, it wouldn't mean anything. So we change to feet per second. Now, we want to know the distance. So what we could say is, in the first 5 seconds, it went 25 feet per second. So 25 feet per second times 5 seconds is approximately 125 feet. Now, that's not an exact amount because it didn't go exactly 25 feet per second the entire 5 seconds. So basically that's a left-handed rectangle because we're using the left side. Now, if I wanted to use a right-handed rectangle, then I would say use 31 feet per second for those first 5 seconds. And if I want to use a midpoint rectangle, then I would use a time of 2.5 seconds. Well, actually, a midpoint rectangle, what I would do instead is I would say use the first rectangle from 0 to 10. The midpoint of that is 31. And the second rectangle would be 10 to 20. The midpoint of that is at 15 seconds. And the third rectangle would be 20 to 30. And the midpoint of that would be at 25 seconds. So, really, now in the book they show you calculating by the left-handed rectangle, which gives you 1,135 feet, and then by the right-handed rectangles, which is the end of the time period, which is 1,215 feet. So you know your actual distance is going to be somewhere in between there. So that's basically it. Have fun with these.